So next we have Alex Hill.
Thanks, Blakesley. So my first exposure to the mess that is the multi-phase interstellar medium was when Carl took me on as a young undergraduate in a very brief summer project in which I didn't get very far, looking at the Millennium survey data, trying to understand how the WNM and CNM interact. And although I didn't get very far, I'm surprised to find myself, however many years later it is now, still thinking about these questions. And I hope that I've gotten a little further than I did at that time, but I remain very grateful, and thank you. So I'll be talking today from a numerical perspective about why is there a three-phase interstellar medium. So we think about the interstellar medium with pictures by various luminaries who are in the room of a mix of phases which may have a hot intercloud gas with warm and cold clouds embedded in it. It may have a warm intercloud gas with hot supernova-driven component of the medium in the inside, or some various mix of these effects. And indeed, more recent numerical simulations, which were pioneered by Miguel de Aveles and Dieter Breschwert, use this basic picture, but create something that looks much more messy than any of the simple original pictures. But these pictures all share something in common, which is that there is a three-phase interstellar medium. We find in the Milky Way and star-forming galaxies that the CNM and the WNM both exist. And as has been mentioned several times so far, this only happens if the ISM is in a very narrow pressure range. If the thermal pressure is above this range, then there will be no WNM. If the thermal pressure is down here, there will be no CNM. And that tells us something about the mean, the typical density in the gas. So if the mean density is around 1, with the heating curve appropriate for, with a G0 of 1.7 or so, a heating curve appropriate for the solar neighborhood, then the mean temperature is thermally unstable. So both the cold and the warm branches of the phase diagram have to be populated. We have to have a two-phase atomic medium. If the thermal pressure, if the mean density were higher, then the thermal pressure would be too high. Again, it's always assuming that the gas is roughly isobaric. Then the pressure would be too high to have a WNM, as I mentioned. And if the mean density were considerably lower, then there would be no CNM. The only observations I will show in this plot, in this talk, unfortunately, are those John Dickey showing that, as Naomi showed earlier in the week, that the CNM exists pretty much everywhere. So somehow the gas must know to be in the stable two-phase pressure regime. And I will try to give some idea about why that might be in this talk. I won't definitively answer that question. I'll mention very briefly that the vertical distribution of the ISM plays very strongly into here, because for a given column density, the mean density, of course, depends on the vertical distribution of the gas. If the gas is very compressed, for a given column density, the density will be high. If the gas is extended, then the mean density will be lower. So your position on the phase diagram is not fixed by the column density of the gas. And indeed, I will argue that the ISM will have the ability to adjust its vertical distribution in order to keep the gas in the two-phase medium, or at least that's our experience from simulations. Okay, so how do we go about this? So I'm using a type of numerical simulation that has become a bit of a cottage industry. in the last 10 or 15 years. Anvar Shukurov showed one set of these simulations yesterday, but we're simulating a vertical column of the interstellar medium, roughly like the solar circle, with periodic boundary conditions on the side, simulating the disk, vertical stratification, so we have gravity that pulls you towards the midplane, and then outflow boundary conditions out the top. The Gent-et-al. Models shown yesterday have a quite narrow disk. We use a very tall column. Both advantages have strengths and weaknesses. But so we are modeling the diffuse ISM with just standard MHD equations, and then all of the physics is right here. We have vertical gravity, diffuse heating, modeling photoelectric heating, optically thin radiative cooling, and injection of supernovae at some approximation of the galactic rate, with some details that will come to matter a little bit later on. And that's all the physics that go into this model. Then I'll mention some groups use cosmic rays, self-gravity, and various prescriptions for the supernova rate. In our case, there was no cosmic rays, no self-gravity, and we set the supernova rate in advance. So we're not simultaneously trying to model star formation and the diffuse ISM. We're modeling really only the diffuse ISM. And when we do this, we get a turbulent-like distribution of gas, but in three distinct phases with different vertical stratification. So the cold gas is the dark blue stuff here in the midplane. The warm gas extends a little bit higher up. It's the greenish brown stuff. And then the pink is the hot gas, where there are hot bubbles in the midplane, but they quickly move upward and fill the volume at large heights. As was shown before, the mass is, by both mass and volume, the gas is segregated into discrete phases. There is some thermally unstable gas due to turbulent mixing, but relatively little. Most of the mass is in the cold gas. Most of the volume is in the hot and warm gas. So the cold gas is confined to very small clouds. How much time do I have? Okay, so how is the structure of the medium defined? So all of these simulations wind up with a three-phase interstellar medium, so cold, warm, and gas and hot gas exist, but how they're distributed varies quite wildly. So here are two different simulations, one on the left, one on the right, from a recent work by Andrea Gatto et al., in which they have different prescriptions for injecting the supernovae. Here they inject the supernovae on density peaks, so the supernovae go off where the density is high, therefore the energy gets radiated away very quickly, and the supernovae are very ineffective at heating the gas. They go off in density peaks, and you'll see there's essentially no hot gas at all in this particular model. Conversely, when they use purely random driving, you get a completely different distribution. These are the same supernova rates, just different distributions of supernovae, where you have the volume is dominated by ridiculously hot, so higher than 10 to the 7 degree gas with very dense, very small cold clouds. So in this model, this would be a highly overpressured, difficult to observe hot gas with confined, dense clouds that, if these models had self-contained star formation, would probably be forming stars like crazy. Steffi Walsh did a bunch of simulations with a range of supernova prescriptions and a fairly small range in, there's the right button, in supernova rate, a factor of 3 or so. And here the hot bars show the volume filling factor of the hot gas. The red bars. The green bars show the volume filling factor of the warm gas, and the cold, the blue bars show the volume filling factor of the cold gas. So if you change the distribution of the supernova, you get a very different character of the ISM. But still, you do get a three-phase ISM. So I want to ask what happens to the pressure in all of these cases. And here we have a rather complicated plot, but this is showing, again, a whole bunch of different models. I have images of density, temperature, and then phase diagrams of thermal pressure, kinetic pressure, and total pressure as a function of density for models in which we've changed the supernova history in various ways. So the qualitative character of the simulations varies significantly. But the point to take away here is in all of these plots, the dotted red and blue lines show the stable two-phase CNM WNM pressure range. And no matter what we do, here we've raised the gravity by a factor of 100. We've turned off supernovae in this case after running them for a while. No matter what we do, the pressure stays in this two-phase pressure regime. So the galaxy, the ISM has no ability to get out of the two-phase pressure regime. I'll throw up the Gatto et al. Plot to finish, and just note that this is the only case in which the Gatto et al. Model is the only case in which we can get the pressure above the two-phase regime, and that's because they have unphysical periodic boxes. So the upshot is if you allow a stratified medium, there is a pressure valve. Gas can go vertically, can relieve the pressure, and maintain the two-phase pressure. And I will leave it there. I meant to leave the phase diagrams up, but I guess I'm not going to. And I'll take questions.
Perfect timing. So, questions? Reading.
So if I'm reading your message correctly, I would take two messages. Let's see if I can remember both. But one of them would be that essentially the pressure is set by the weight of the material, and pretty much regardless of almost anything you do inside.
Well, I'd invert that a little bit, because here's the weight, and the weight can change. So the ISM can change the weight that in the way it needs to get to maintain the pressure, because the thermal pressure is a minor contributor to the vertical distribution. It's the turbulent pressure that really matters. So the thermal pressure adjusts itself. There's more variation in the turbulent pressure than there is in the thermal pressure.
And then the question would be, so what's your explanation for the pressure to remain in that range for the thermal pressure?
So we're still looking at it. I wish I had an ironclad answer, but it's got to be set by the interaction between the imposed diffuse. So we impose the diffuse heating rate and the cooling function. So part of it is that the cold gas mass has to stay somewhere, because if there's enough mass in this box that the medium can't be fully warm, and then some gas has to be cold, and then if gas is cold, then if it has to be reasonably dense. So if it was over here, then it's going to heat up to the minimum CNM pressure. So any dense gas has to get up to will get heated because n gamma is greater than n squared lambda.
Question back there? I'm kind of curious if you could extrapolate to other parts of the galaxy, like the far outer disk, or closer to the galactic center, to get control out of.
Well, I mean that's what we're trying to do here. Is this case where we've significantly increased the gravity, it was an attempt to model a part of the galaxy where the surface mass density from stars or dark matter is much higher, and it doesn't really change things much. And we've also looked up in HVC environments, so high velocity cloud environments, where the radiation field is lower, and then the equilibrium pressure drops, but so the stable range is lower, but the gas still largely sticks within that pressure range.
Okay, so that's all the time we have for questions. Let's thank Alex again.